Okay. So we continue. Okay, we haven't discussed other problems. So our next problem I want to discuss is about the maximum rate of change of a function. Okay. So let f of x, y sine x, y, and we have to find out the maximum rate of change of the function f at the point when 0. Okay, now in my previous class, I already mentioned the formula. Okay, but let me repeat again. So the for unit vector, okay, and there's a directional derivative of a function, okay, at the point when the 0 is given the gradient of the function at this point times the derivative. Last time the dot product was a unit vector. This is always less than or equal to the length, okay? And then this is the maximum value, okay, actually. And the equality holds if u equals this vector, then normalize it, okay? Here we're talking about unit vector. So in order to find the maximum rate of change, this is the maximum rate of change, okay? The maximum rate of change, okay? And in which direction? And you can figure out the direction also. The direction is the normal, the gradient, okay? So this is it occurs in the direction, right? It occurs, yeah. It occurs in this direction. Okay, great. So that's a picture, very clear. So now let's look at the gradient. The gradient of the function, it's going to be the partial derivative, right? That's just routine. Let's calculate. So it's going to be when you differentiate sine xy with respect to x, you get a y cosine xy. Okay. When you differentiate with respect to x, with respect to y, you get x cosine x and y. Okay. So let's evaluate at the point when 0. So when y is 1, when y is 0, that's a 0. Okay. When x is 1, then that's 1 cosine. Yeah, it's 1. Okay. So that is a direction. Okay. So you can answer the question now. The maximum rate of change of f is, okay, is the length of this, which is going to be 1. Okay. And it occurs in the direction of u, which is the gradient of f, and you normalize it. But this is the length is also, this is unit vector. So this is a complete answer. Okay. Okay. Our next problem is about maximum value, absolute maximum value, and minimum value. Okay, this is will be also possibly covered because it's very important. So find, but I'm not going to make the boundary very strange, okay, in the domain. I probably use a square rectangle. This. So find the absolute maximum and minimum values. Okay. So this is a continuous function. It's polynomial. Right. Sorry, just 2x. Okay. And this is a function on the domain D. This is a domain actually is going to be x is between 0 and 3, y is between 0 and 2. Now this is actually is a rectangle. Okay. So the function must have absolute max value and absolute minimum value. Okay. So how do you find it? And the important factor here is here's the important factor still, right? F attains the absolute maximum value or minimum value, okay, either at critical point, okay, inside D or on the boundary. Now, on the boundary, sometimes we face another problem, right? On the boundary, and the boundary is a curve, consists of 4 pieces here, okay? Sometimes you can find the boundary directly, sometimes you have to, if like a boundary is a circle, then you probably use called a Lagrangian multiplier to find the maximum value on the boundary. Okay. So there are a couple of choices here. So let's look at this. So you need to find the partial derivative. Find the critical points first. So it'll be 2x minus 2y plus 2. Okay, this will be just a negative 2x. Okay, you set this to be 0, and clearly x is going to be 0 from the second equation. When x is 0, y is going to be 1. Okay, so that's only one critical. Let's check. Yeah, this is only one critical point, 0, 1 inside this domain. Okay, where it is, let's draw it. Okay, this is not inside, it's on the boundary. Okay, it's like that. Okay, this is 3, here's 2, and this is 0, 1. So you don't need there's no critical point inside the domain. So it's actually on the boundary. So all you needed to do is just focus on the function on the boundary. Okay. The function must attain a maximum value on the boundary. Okay, because there's no critical point inside the boundary, inside the domain. Okay, you do find the critical point, but this has happened to be on the boundary. Okay. All right, so now all I have to do is to find the value along each side. I don't want to, this is a square, so it's easy. You don't need to use called a Lagrangian multiplier to find the maximum value. Okay, and this is not a small curve, just consists of 4 pieces. Okay, so let's take a look at the first one. Yeah, along the boundary. Okay, so x is between 0 and 3. Y is 0. Okay, so in that case, the function, okay, becomes when y is 0, so I only have 2 terms. Okay, So this function I can modify. I can get x plus 1 squared minus 1, right? So for x between 0 and 3, what is the maximum value? What is the minimum value of this function? Okay, and it's clear that if we draw the graph, okay, this is a if we draw the graph, let's call this function. Yeah, you know, I can use another. I cannot use yeah, just use z. Okay, z and x, right? So x, yeah, the vertex is here. Okay, when x equals 0, this is a parabola open like that. So for x between 0 and 3, clearly the value, the function has a maximum value and a minimum value, right? Yeah. This function, the maximum value is going to be when x equals 3. It's 15. The smallest value is when x equals 0. So which is 0. So that is a maximum value, minimum value. It's very clear, right? Second, and x is between 0 and 3, and then y equals 2. When y equals 2, the function this function now becomes x squared minus 2x, and put 2 here, right? Plus 2x. So after you simplify it, you get minus 2x here. Okay. So you can also write like this: x minus 1 squared and minus 1. Okay. So the graph looks like that. If you want to draw the graph for this function, here's x, here's y. X is between 0 and 3. Okay, and this is a 1. Okay, and this is a parabola. When x equals 0, that's a 0. So it's passing through that point. Okay, now look at this picture. You will see that what is the maximum value, what is minimum value, right? So clearly, the maximum value is when x equals 3. 3 minus 1 squared, and that is 4 minus 1 to 3. So that's the maximum value. The minimum value is going to be actually, yeah, when x equals 1. Okay, 1 minus 1 square minus. So that is the minimum value. You see, look at the picture, right? Yeah, that's 4 pieces. It's a little bit complicated. Yeah. All right. Then you look at the 2 vertical lines boundaries. So when x equals 3y between 0 and 2. When x equals 0, let's still look at the one on the left hand. Yeah. So the function is going to be, it's going to be, well, look at when x equals 0, every term contains x. So it's going to be identical 0. Yeah. When x equals 0, yeah, look at the original function. Yeah, every term contains x, so it's 0. That's easy. Okay, so the maximum value, that's identical. The fourth one is when x equals 2, when x equals 3. Okay, in that case, f of x, fxy is going to be 3 squared minus 2. 3x becomes 3, okay, plus 2, 3. So you simplify it, you get 9 plus 6 is 15 minus 6y. But this is a linear function. Now for the linear function, right, what is the maximum value, what is the minimum value for x, for y between 0 and 2? When y equals 0, so you get 15. When y equals 3, and when y equals 2. So that is a 3. So, okay, so you get pretty good idea around each side, yeah. So this is, let's go back to this picture again. So you have you have this rectangle, right? Okay. So the function is always equal to 0 along this line, okay? And around this line, the function is between 15 and 3. Along this boundary, okay? Along the boundary when y equals 2, actually the f is between 3 and -1 somewhere. So when the function is on the axis, it's 0 and 15, 0 and 15. F is between 0 and 15. So it's very clear. The function here is 0 on the vertical y-axis. And then here from on the axis is from 0 increase to 15. So this is the maximum point. Then from 15 you decrease to 3. And here then you decrease to -1, then increase to 0. Okay. So this is a kind of picture, you know, and you can tell that, right? You can tell that the absolute maximum value of f is going to be 15. Okay, it occurs, okay, at the point 3 and 0. Okay. And the absolute minimum value will be -1, okay? This is -1. It occurs at, I think it's -1, right? So it occurs at 1, and the y value is 2. Okay, okay. So that is a point. Yeah. Okay, so that's 2 points. Okay. Yeah, I wish to have examples also have a critical point inside domain. In that case, maybe we consider the circle. Yeah, consider the circle on the circle, you know, a function. Usually it's a linear function on the circle. Yeah, let me give you. Yeah, let's discuss one examples. Yeah, okay. Okay. Okay, so given a function, this is x plus 2y, right? On the domain D. Okay. Find the absolute, the maximum, and the minimum value. Okay. Now for this problem, yeah, this one is so there's still no critical point in the domain. All you have to do is find the maximum value, minimum value. But this is a circle, okay? So so the boundary will be just a circle. The domain is a disk, we call it. That's the difference between domain. Okay. So first, yeah, we just repeated the above, okay? So there's still no critical point in the domain, okay? F x is going to be 1, yeah, the partial derivative, and this is going to be 2, so that never be 0, okay? No critical point anywhere, okay? So the function, so then you conclude that f attains the maximum value, maximum or minimum value on the boundary, okay? So the question is, how do you find the maximum value, minimum value on the boundary? If the function occurs, attains the maximum value somewhere, okay? Not necessarily absolute maximum value, somewhere. And then this, you can use a Lagrange multiple to find it, okay? So you have to find those points and compare, right, the values, okay? So what they have to do is a couple ways to do from here. You either change the function, either restrict the function to the boundary, and then you look at it as a function with one variable, okay? And that's also possible, okay? So the method one, to find, just, parameterize the circle, cosine t, y equals sine t, okay? So f x y is going to be f cosine t sine t. Then you get a function for one variable, okay, which is going to be cosine t plus 2 sine t, okay? Then you're trying to find out the max. So this is another function, this is just a function. T is let's call it a g of t, okay? T is between 0 and 2 pi. We just need to find the maximum value, minimum value of this function, new function, one variable on the interval, right? It's a periodic function. Let's just look at this on the interval. So g prime t equals negative sine t plus 2 cosine t. Then you solve it, right? Find a critical point. So this is it's equal to 0. Then the equation you will get, okay? The equation you will get is it's probably not maybe we cannot even find the tangent, okay? The angle. So this is just solve the equation. So cosine t, you get a tangent, okay? So you get tangent t, okay, equals, tangent t is sine t over cosine t equals 2, okay? So for what kind of angle you get a positive value? One is this one. Another angle here is both sine and cosine are negative, right? Either this or that angle. That's two angles make it tangent t equal 2, okay? So t is going to be arctangent 2. That's the first solution. Another solution will be just pi plus the angle, okay? Then you look at the value of the function. You look at the value of the function, okay? And you compare which one is larger. And you also have to look at the endpoints. So you have to find out what is the ft1, right? GT1, and you have to look at GT2 and 0 and the G2 pi, okay? Now G0 is easy to this. It's going to be 1. When G2 pi, it's also going to be 1, okay? Okay, but the GT1, maybe it's not easy to find out. But how do you do that, GT1, okay? So this is a T1, smaller, right? So tangent equals 2, that's a 2, here's a 1. So this will be square root of 5. So this then, cosine t is going to be T1, 2, sine T1, cosine T1 is going to be 1 over square 5 twice. It's 2, and the sine will be 2 over square 5. So it's going to be, add them together, 5, right? 5 square 5, so the answer will be square 5. And the GT2 is going to be cosine T2 plus 2 sine T2, because this case, they both are negative, so I just put an answer here, negative 1/2, okay? So now it's pretty clear, right? The absolute maximum value of G is given square 5. Absolute minimum value of G is square 5. That's also the absolute maximum value of F. So you can see that absolute maximum value of F is going to be square 5. Okay, you can also tell where it occurs. Okay, it's on the boundary at this angle. Okay, so it occurs when x equals when x equals cosine t, y sine. Okay, it occurs at x1, y1, and x is a cosine. X is cosine t1, so it's 1 over square 5, and y is equal to 2 square 5. Okay, yeah, that's a cosine t1 and sine t1. Okay, and then the absolute minimum value of f is going to be negative square 5, and it occurs at the point x2, y2, and it's going to be just negative. Okay, it's just the opposite direction. So this is a graph. It's a circle, and somewhere here the function has a maximum value, and somewhere here the function has a minimum value. It's because the function is a linear function, so it's just opposite. Okay, and the value here f is going to be negative square 5. Here's f equals square 5. But so that's about maximum value, minimum value. Let me find another problem. Okay. So now we're going to focus on double integrals. Okay. So here's a first question. Double integral. Set up an iterative integrals. Iterative integrals for this double integral. Okay. So it's y squared e to the xy dA. D is bounded by y equals x, y equals 4, and x equals 0. Okay, you needed to set up both of them, okay, and evaluate one of them. Then you decide, which one you want to evaluate. Okay. All right. So first of all, you have to draw the picture, okay, the domain. Okay, let's see. Y equals x, this line. Y equals 4 is this line. X equals 0 is this line. So don't make mistakes. This is going to be the domain. Okay. This is a domain. Okay. So the intersection point here is a 4 and the 4. Okay. Here's 4, 0 and the 4. Here's this point 0 and the 0. Okay. Now you're going to evaluate this double integral over this domain using iterative integrals. So the first case, okay, you fix x okay? Fix the x, then you will see the y value changes, right? So fix the x, you draw the vertical line, and you want to give the range, the range for the y value of the points on the. This is going to be x and the y, okay? When x is fixed, the y value, clearly the upper bound is still 4. The lower bound depends on x, just x, okay? So using that, then this double integral is going to be, first of all, from 0 to 4 and put dx here. Then dy, and the y is from x to 4, and this is y squared e to the x times 1, okay? The second one is we're going to fix the y value. It's between 0 and 4, okay? Then let's look at the picture again. And this time, the y value is changed, fixed, okay? But the domain is between, yeah, this is domain, right? Yeah, this is domain. So you needed to look at the point on this horizontal line, and what is a lower bound for x? Lower bound for x is clearly 0, and the upper bound for the x it should be expressed in terms of y. That's just y, okay? So yeah, it's y, okay? Because this is a line y equals x, x equals y equals x, okay? So the upper bound y is fixed, remember, okay? X is between 0 and y, okay? So the double integral can be, yeah, this is a y from 0 to 4, and that is from 0 to y squared e to the xy dx. Now let's take a look at those two iterative integral. Which one looks much simpler, right? If I evaluate the above one with respect to y, I have a y squared in front of e. You view x as a constant. I think this is more difficult, okay? More complicated at the starting point, okay? So if you consider this integral, it'll be easier, okay? Much easier. So that's why I use this integral, okay? The entire derivative of y squared e to the xy, okay? If y is a constant, so we will add y e to the xy, okay? Because when you differentiate with respect to x, you get y squared e to the x times 1. Okay. So finally, we will get y e to the y squared minus y e to the 0 times 1. Okay. Okay. Then you find the antiderivative of this function. The antiderivative of this first function is also used. You can use a substitution. By guessing the trine, you should get this, and when you differentiate, you get the y, okay? And this is half of y squared. And then you evaluate this unit, okay? So now I'm going to get e to the 4 squared minus 4 squared and minus 1/2 e to the 0 minus 0 squared. Okay. So this is the answer, final answer. Okay. Yeah. Our next problem is about you are given the iterative integral, and what I want to do is I want to change the order of the iterative integral. Okay, then you have to figure out the region of the integration. So sketch the region of integration, and changes order of integration, because sometimes if you change the order of iterative integral, right, then maybe much easier to evaluate the integrals, iterative integrals. Okay, so this is you are given this iterative integral from 0 and square 4 minus y squared. So you are given the function. I'm not asking you to evaluate, so that's why I don't give you a specific function. All right, but you have to understand this iterative integral. All right. What does that mean? Read this integral. So y is all side. So that means for each fixed y between -2 and +2, the x value is between 0 and the square 4 minus y squared. Okay, right? So that means you have to look at this equation. Look at this equation, the upper bound. Okay, this upper bound actually, and this is a if you square it, you will get an equation, a typical equation for a circle. Okay, so but it's probably only partial of the circle. I think this is only the circle you're talking about. Okay, okay. For y between -2 and this is fixed y, and the x is between 0 and square root of 4 minus y squared. Okay. Yeah. Okay. Yeah. Yeah. You solve for x, and you get the upper bound for the x. So this is our domain. Okay. So this is a domain D. It's a semicircle. I can describe the D in another form. I can say this is a square as a circle less than or equal to 2 square, and I just assume that x is greater than 0. Okay, that's another way to describe. So that iterative integral is going to be, yeah, this integral from -2 to +2 from 0 to 4 minus, yeah, f xy dx dy this is a double integral of this function. Then that's our middle, right? This is our original integral. Okay. Then you can switch the order. Okay. To switch the order, I needed to fix the maximum value for x is 2. So here you fix for each fixed value x between 0 and 2, right? And what are the possible values for y? So then you have to look at the horizontal vertical lines. Okay, this is the x, right? I think the upper bound for the y value should be square root of 4 minus x squared. But the lower bound for the y value is going to be negative, because when you solve for y, you get a plus minus y value, right? So, using the equation, solve, yeah, and we saw solving this equation for y variable, right? So you get upper bound, lower bound, okay? All right, so now it's clear. So this is the x, that's outside. Inside the y should be from right, so that's it. Now, in general, it's difficult to evaluate this kind of integrals, honestly. Okay, so let's take a look at this integral. I just think about any functions, okay? So we can evaluate this double integral d, and this time I'll give you a very specific function and dA, okay? And well, what is d? D is the same interval in same region I mentioned above. Okay, x is greater than 0. Okay, so we're going to evaluate this. Now you can use one of the iterative integrals and to evaluate. Okay, you can also, if you have to use but another options, because the domain, the region is a semicircle, so it's a very good region for polar coordinates. Okay, so we can try both methods. But if you are asked to use a polar coordinates to evaluate, then you have no choice. If I do not mention, then you have two options. Maybe you can use a traditional iterative integral to evaluate. Okay, so let's write down both. I think both works. Okay, so the first one is going to be the iterative integral is I think the y is from -2 to the +2, and the x is from 0 to 4 minus y squared, right? And this will be x squared plus y squared minus 1, and that is the dx, right? That's dy. That's what we got here at the very beginning. Yes. All right. So now let's see if we can evaluate. Otherwise, we stop. Okay. Oops. The file is gone. And, right back. Yeah. Okay. So let's find the antiderivative, okay, of this function with respect to x. Then that will be x cubed, see? And that is y squared x minus x, right? This is antiderivative. Okay, and as you can see that it's really get complicated. It's a 4 minus y squared, and that's a square root, right? And then cube. See, y squared and square 4 minus y squared, and now I think it's complicated. Okay, right? No idea what is the next step. You know, you can use substitutions, blah, blah, blah. You can try to make it simpler. It's possible. Okay. However, it's getting complicated. Okay, it takes more time. It's easy to make mistakes. So even I do not ask you to use a polar coordinates, and you shouldn't continue here. Okay, so we stop here. Okay, and then we try use a polar coordinates. If we use a polar then we use a polar coordinates. Okay, using polar coordinates, x equals r cosine theta, y equals r sine theta. Okay, remember, right? Then, okay, let's see. So this is our circle, right? And then here I'm going to use r and theta. I want to see what is this is a d, what is d bar, right? So which I can send it to here, right? Clearly, theta is between negative pi/2 and positive pi/2, right? Because this is the angle theta, right? This in this case is negative and going around, and I is between 0 and 2. Okay, for an arbitrary point here, here's a right. This is r. R is the largest value for I is going to be negative. Is going to be 2. Smallest value for I is 0. So I is from 0 to 2. Theta is from negative pi/2 to positive pi/2. So you get a rectangle. That's my d bar. Okay. Now it's very clear. Okay, we already know that. Yeah. So that d bar is a pre-image of d under this transformation. Okay, this is a transformation. It changes a rectangular region to a semicircle. So what we're trying to do is, it's kind of, this is a two-dimensional substitution integral. So here you have a double integral of the function, right? And then this is the pre-image, the integral. Okay, where it's from? It's from the rectangle. It's much better. Okay, so here's f r cosine theta when the place sine theta. But don't forget to put the r here, d bar. Okay, so this is a factor. Don't miss that. I want to see that first before you do the evaluation. Okay. Then the problem becomes easy. Okay. Okay. This is kind of transformation. You know, you live in the current world. It's it's a semicircle here, and your pre-life. Okay, your pre-life is in another space. Okay, different coding system here. Okay, they look quite different. It's a square. It comes from a square. The semicircle comes from the rectangle. Sorry. Okay, so now, okay, so so let's simplify the function first. The function is x squared plus y squared. So x squared plus y squared is just r squared, right? And minus 1r, and then d bar. So, and our domain is also a rectangular domain, so you can use any of this. So from negative power to any order, okay? From 0 to 2, r squared minus 1r, dr, and then d theta, okay? So you see, it's very simple, okay? It is very simple, okay? So you get negative power 2, positive power 2, and this will be r cubed minus r, right? And then antiderivative is a quarter of r to the fourth, half of r squared, and evaluate. Okay. Then you get a constant here, right? Quart 2 to the fourth power. Here's 2 squared, okay? And d theta. All right, let's look at what's inside. Okay. The first term is 2. 2 minus 4, sorry, 16. 16 divided by 4 is 4. 4 minus 2 is 2. Okay, d theta. And then that's just the 2 pi. Okay, so 2 pi is the answer. Yeah, 2 pi is the answer. Yeah, that's a good example, I think I have discussed all kinds of problems I'm supposed to cover, most important problems on the test. So I would like to stop here. Yeah, this is so how do you go over those problems when when you look at my notes, right? And first thing you have to do is look at my notes. Don't look at the solution and redo it by yourself. Okay, that's the first thing you have to do. Redo it by yourself, and then if you can get same answers, great. If you don't, then read it. Okay, if you just want to read the solutions and it sounds like you understand, but does not help you too much. Okay, you have to do similar problems from the textbook for practice. Okay, if you're not able to do that, understand it's not So I do not always encourage students to get a tutor immediately to do all the type of problems. You have to spend some time. Sometimes you need to spend about 10 to 15 minutes on a particular problem to figure. If you can figure it out by yourself, look at the examples in the book, look at the example in my notes, then you will memorize the idea. So if you just ask somebody show you how to do it, and you sound like understand, then you put aside. And the exact same problem, if I put on the test, you probably still cannot do it. Okay, so this is a first step. Then you look for the similar problems on the textbook for practice. Those problems similar to the ones similar type of problems I discussed in the class. Okay, if you're able to do most of these problems, then you're fine. Okay, I found out many of you do well on the quizzes. Okay, so only a few of them don't get the high scores on the quizzes. So take the series and make sure you do all the homework problems. Okay, this is spend some time this weekend and don't miss the test. Okay. Now it's quiz time.